Well, Arvin, thank you, and thanks everybody for listening to the talk. Um, well, this verification and validation has been mostly the central part of several talks. So, but allow me to go back to some basics about this just for a few minutes. And because I want to stress that in this realm of validation and verification, there are several ways of looking at it and looking at them separately, either from the conceptual model side or from the simulation model. And then also when we compare either simulation as an engine to reproduce data, and when we compare or when we want to validate our assumptions about the real world. So on what we have been discussing so far, we have been focusing on the left semicircle of what I'm showing right now. And I guess for the audience of peer, what matters most is that quadrant of the operational validation, which means when we actually are comparing two observations, right? So most of what we're going to discuss is about this part, but then I don't want you to lose track of the fact that there is also validation for the formulation and verification for the methodology, more than the verification for the implementation and the operational validation, which is what we mostly are concerned about. And then I'm going to start also going back to 2010 on some legacy work that we did for ShakeOut verification, which was the first step we took as an effort led by SCEC, by the Southern California Earthquake Center, when we took 3 codes and did comparisons of results for the ShakeOut scenario. And this led at the time to figures like the one I'm showing right now, when we could see that all 3 codes were ready to run independently because they were leading to the same results. And well, we did all sorts of comparisons. Here are some qualitative verification, meaning that we are only looking at figures, but we also quantify this in terms of numbers. And for that, we did verification of the traces of the synthetics. And then later on, we focus on using measures like the ones proposed by Anderson and Kristekova. Usually using Kristekova et al. Work for verification, meaning for comparison between codes. But then when we are focusing on validation, we resort to Anderson because it's more practical and it gives everybody like a good sense of what we're dealing with. And then years later, we went on to using Chino Hills, the 2008 earthquake in Southern California, as a good example of what we could do if we went to higher frequencies. And then later on, we expanded this, as I will show you later, for a larger number of earthquakes. Then when we did our initial work for validation for Chino Hills was independent. And then later on, we also did verification for Chino Hills at higher frequencies. And here is some example of the agreement between the 3 codes, Hercules, the code by Graves, and the code by Olsen and Day and Sui, in which we were able to achieve good agreement even at higher frequencies. This is not trivial work, and we actually haven't been able to complete it yet because we've been working on it for years. This is an image from a poster 5 years ago. But then we took this to validation and we compared to over 300 of stations for the case of Chino Hills. Obviously, you get all sorts of results from very good to very poor comparisons. The very good being, for instance, the one at the top left, and the very bad comparison being at the bottom right. And we do comparisons for energy measures, for intensity, for response spectra, for Fourier spectra, as I am showing right now. And again, you get all sorts of results, and these are comparisons for large number of observation stations. And what the Anderson measures allow us to do also is to synthesize information in a way that is meaningful and convey a message easily understandable by everybody. So these are what we call the goodness of fit maps. Uh, these are comparisons for all three components and for the whole breadth of the spectrum, 0 to 4 hertz. And what we can also do is we can separate those comparisons for different frequency bands and understand where the models and the simulations are best. And obviously, at the lower frequency, this physics-based or numerical representation of reality gives you a much better result than when you go to the higher frequency. That doesn't mean that when we look at the signals, they are not they don't look realistic at the higher frequencies. They also look realistic, but obviously they don't match the data that well, right? So here, what do you see is the lighter the color, the better the match, and the darker the color, the poorer. Then what we realized doing this work is that the velocity models, as I will conclude at the end, matter a lot, and is possibly what matters most. And this is Dominique Asimaki shows a figure similar to this because the different velocity models that we have for these regions have significant differences, and also they can differ a lot depending on what alternatives you use for each model. And what we find is that then that obviously is reflected in the results of the synthetics. And when you compare this for different goodness of fit maps for the different models, then you get different results, some of them suggesting that one of these models perhaps performs better. So in order to understand, another way of looking at this is in terms of attenuation. And I think Kyle Withers showed some interesting figures about this yesterday as well. And now what the goodness of fit maps allow us is that we can then automate this process for several earthquakes. And what we did is to repeat basically what we did for Chino Hills for 30 different earthquakes. And then you get lots of goodness of fit maps, and then you can synthesize information, and eventually you get to a figure like this one in which you can basically summarize the results in a very simple way and understand which model leads to the best possible result of all the earthquakes that we compared. There is a caveat though, which all these 30 earthquakes were low magnitude earthquakes because that's the data we have available for the region. And obviously then we work under linear and elastic conditions, and that has some implications as well. Now, if you think of what we can do for 3, 4 different velocity models, then now think of what we can do for different parameters that we use in this simulation. So we also did work for using different velocity models, different minimum velocity, shear wave velocity, using different number of points per wavelength, using different attenuation parameters and different source parameters. And obviously, all this leads to many ways of comparing these results. Here, what I'm showing is a possible combination just for 2 different velocity models. So it's a figure that is similar to the one that I showed before. And the one on the right, the one with the purple and orange colors, what allows you to see is which one performs better in a particular area of the modeling domain. Now, when we do this for all these possibilities that I mentioned before, then what you get is that you get some of these surface maps that allow you to compare different parameters. I'm not going to get into the details of which one is S1, S2, S3, S4. What I just want you to take away from this figure is that when you have the means to automate this process for several simulations, different earthquakes, different parameters, then you can do comparisons in order to understand which of those factors involved in the simulation affects more or more significantly the validation results. And that gives you some insight about where to put your effort, right? And then about that, I'm going to do some preliminary remarks, and I'm going to come back to a similar slide at the end. So what I'm going to say so far is that the velocity model seems to be what matters perhaps the most of all these. The minimum velocity matters only in terms of how high you can go in frequency and how much of you want to put effort on the computational resources. And obviously the numerical simulation, the numerical resolution also matters a lot for verification, but it doesn't matter that much for validation. And I know that this is a controversial statement perhaps for some of you. What I have found is that at the higher frequencies, there are so many factors involved that adding a lot more of points per wavelength won't take you that much farther away. And there are other factors that matter most. The attenuation model matters significantly, especially for far field analysis and for higher frequencies, which is somewhat perhaps intuitive as everything in this slide. The source model, something that surprised us when we were doing the verification for Chino Hills at higher frequencies was that the source model matters more than we thought at the beginning. We thought that even for a small earthquake, we thought at the beginning that for smaller earthquakes, having an extended source model wasn't that much important. And it turns out that it matters, and it matters significantly in order to get good results. And obviously the source uncertainty as a consequence of what I just said it can make a significant difference. Now, there are other aspects of interest that I wanted to highlight. One, having these automated workflows in order to do the simulations efficiently, combining many different parameters is important and is something that should matter to the community. In order being able to develop the capabilities computationally in order to take on this kind of work. Another one is that the measures that we use to indicate how good is the validation are also important, but we don't need to focus on a large number of measures. There are some that are more important than others. There is this aspect that the urban environment affects the results of the observations, and I mean that influence the data, and perhaps by extension it can influence the validation. Obviously, nonlinear side effects that others have mentioned before, and topography. Now, what I mean by workflows is that when you get to workflows like this one that I'm showing you, is what allows you to combine different simulation capabilities. Here is a combination of the broadband platform from SCEC with Hercules in order to improve the low frequencies and to use the capabilities of the broadband platform in order to select the best possible source model. So the BBP, you can do many simulations rapidly with the BBP in order to get to which one of the realizations of the source models is the best realization, and then come back to use that source model in order to do 3D simulations, and then combine the results of the 3D simulations with the 1D simulations of the BBP. So these are the kind of things that you can do if you can combine different simulation codes and different applications. My mentioning about the alternatives to reduce validation post-processing is that using some machine learning techniques, we were able to identify that perhaps the two measures that matter the most are response spectra and energy. And that will allow us to do better validation more efficiently in order to reduce the post-processing analysis. And another of the additional aspects that I mentioned before, this is a more recent work from, well, it's now 3 years, but the importance of the built environment. We have done simulations also including building models, obviously simplified building models, but then from this we get something that is important for us in terms of the ground motion is that in an urban environment, data can vary a lot because of the presence of the buildings. And And that is an aspect that introduces additional variability to the comparisons and to the data, and everything combined is important to consider. I won't mention more about the nonlinear and topography because others have done so. So I'm going to come back to the concluding remarks and mention again, I think what matters most is the velocity model. And what I'm going to mention about that is that if you get a good velocity model, then there are other factors that cascade after that you will probably get better results if you make an effort to get a better velocity model. So that's why I'm highlighting that as something more significant than other factors, because it influences the minimum velocity, it influences your numerical resolution. The attenuation model usually depends on the VS values, and then you will get better attenuation as well. If you get a good velocity model, your source inversions are likely better. And then obviously you get better data to infer nonlinear addition to the 3D simulations. And then last, you probably get much better results when you include topography if your velocity model includes the shallow crust with good resolution. And I think several of the previous speakers have mentioned points about this. Now, under those optimal conditions, and this is something that I want stress as the last part of my presentation, is that when things are right, the results from validations are very good. Here is a comparison for 3 of the stations that included in the simulation for Chino Hills at 4 Hertz. You see comparisons of the velocity traces, of the amplitude of the traces over time, measures of the energy as it progresses in time, Fourier amplitude, and response spectra. And obviously, there is a lot more to say about this in terms of that many good signals can also lead to many bad signals, bad synthetics. But overall, when the conditions are right, the results are much better. Some final suggestions or things that I think that the community should care about are inversion is something, the tomography, the 3D tomography is probably key for the future of ground motion simulations in this work, because that's what is going to improve significantly the velocity models. And we have, probably don't have the time to go into detail, but small improvements, even very tiny improvements in the velocity models lead to significant improvements in the validation results. And we have seen this because of the inversions that have been done before for Southern California and how they have impacted positively the results in terms of validation. An aspect that we don't know that much or how to control that well is anything that is related to energy losses and elasticity, nonlinearities that are important. Variability and uncertainty. I think the variability because of topography, because of the urban environment, there are several factors that can increase the variability of the results, and that will impact how we perceive the validation. Uncertainty, I think something that perhaps some of you will give high value is we need to figure out how to carry forward uncertainty in the simulations from the source through the wave propagation, and then the final results that matter for risk analysis.
1 minute, Ricardo.
Thanks, Arvin. And then this will only be possible if we can build these computational workflows that integrate different components. So I think what Dave presented, Ahmed El-Gamal before, and Rob Graves and others, and perhaps what I show you today highlights the importance of continuing this work in terms of building these computational workflows. So finally, I'm just gonna thank this wouldn't have been possible without the support of SCEC and several of members of the SCEC community. Most of this work was initiated at Carnegie Mellon, and Jacobo Bielak was a mentor and a leading force in this. And then obviously the agencies and the computing facilities that make it possible. That's all for me, Arben. Thank you.
Thank you very much, Ricardo. This was very interesting. I like the history of, you walked up back almost 20 years ago when we started these validations. It's